Today's topic is resistances in series and parallel. In the previous class, we have discussed about Kirchhoff's circuit laws. We have seen that there are two Kirchhoff circuit laws. One is Kirchhoff's current law, which states that at any node in an electrical circuit, the algebraic sum of the currents is equal to 0. And also, we have seen Kirchhoff's voltage law, which states that in a mesh, the algebraic sum of voltage drops across all elements is equal to 0. And we have solved problems on these things also in the last class. In today's class, we will discuss about resistances in series and parallel, how to minimize or how to determine the equivalent value of the resistance. But before that, let's have a quick recap question. See, this is based upon your KCL and KVL. See, there are three resistors having resistance of 100 ohms, 200 ohms and 300 ohms. These are connected in series and connected across 250 volts supply. Determine the current which is flowing in the circuit and the power which is dissipated in each resistor. See, if this is the current which is flowing in the circuit, I is the current which is flowing in the circuit, you know what is the voltage drop which is created here? As per Ohm's law, V is equal to IR, right? So the current which is flowing here is I into 100. So it is 100I. Here it is 200I. Here it is 300I. Right. This is, I have applied Ohm's law. Now let us apply KVL now. As per your KVL, the algebraic sum of the currents in a closed mesh, in a loop, is equal to 0. The algebraic sum of voltage drops across all the elements is equal to 0. See, in this one, if I start from here, top left, how many elements are there? 1, 2, 3 and 4. So 1, 2, 3 and 4, and the sum of voltage drops is equal to 0. So I will start from here and I will come back to here. So if I am moving from plus to minus, I will take it as plus. If I am moving from minus to plus, I will take it as minus. So now I will start from here, plus to minus, 100I plus 100I, again plus to minus, plus 200I, similarly plus 300I. But here, when I come to here, I am traveling from negative of the battery to positive of the battery. So I will take it as minus 250, isn't it? So now if I solve this thing, see, 100I plus 200I plus 300I, it is 600I. Minus 250 is equal to 0. So I is equal to 250 by 600, isn't it? So 5 5s are 5 12s. So the answer is 5 by 12 amperes. This is the current which is flowing in the circuit. Now, if you want to determine the power dissipated in each resistor, we know the formula also, right? The formula is I square into R in any resistor. So for all these resistors, the current is same, only the resistance is varying. So if I take first one, 100 ohms resistor, the current is 5 by 12 whole square into 100. For the second one, it is 5 by 12 whole square into 200. For the third one, it is 5 by 12 whole square into 300. This is the way how we solve these problems. Okay. So now let us move on to determining the equivalent resistance. Equivalent resistance when we do have too many number of resistors in series and parallel. So I'll start with the basic introduction, and then we'll move on to resistors in series and parallel, and then we'll move on to simple numerical problems. So coming to the first one, see, as already said in the previous classes, a resistor is a passive two-terminal electrical component which implements electrical resistance as a circuit element, isn't it? So resistors are actually meant for reducing the current flow and the lower the voltage levels within the circuits. Most of the times, any circuit can be having more than one resistor to limit the flow of charges. When we do have multiple resistors, the simplest combinations are resistors in series and parallel. There are other combinations also, but let us confine to series and parallel resistors. So before we go for this resistors in series and parallel, First of all, let's see how these resistances in series are. So this is a representation of resistances in series. Now see here, I'm considering a circuit where there is a 1 voltage source V and there are 2 resistors connected like this. These resistances are connected such that, see, same current is flowing in them. Okay, these type of resistors which carry same current are considered to be in series. Try to remember this point. Set of resistors which carry the same current are considered to be in series. This is the fundamental thing. Okay, so now let us determine the equivalent resistance for these series connected resistors. Now let the voltage drops across them by V1 and V2, right? Now I will draw it. See, right? This is V, this is I is current is flowing, this is R1, this is R2, and this is V1 and this is V2. So the voltage drops across this are V1 and V2, and the current flowing in them is I. So applying KVL, see what is the starting from top left. What is the one? This is V1. Again plus to minus, this is plus V2, and here I am going from minus to plus, it is minus. This is what I have written. So rearranging the terms, I closed here, V1 plus V2 is equal to V. You know V1 already I do have. What is V1? By Ohm's law, V1 is equal to I into R1. Similarly, V2 is equal to I into R2. So if I substitute them, see V1 is equal to IR1, V2 is equal to IR2. If I substitute them and take I as common, I'll get R1 plus R2 is equal to V. Okay, so this particular, so what is the net voltage in the circuit? V. What is the net current in the circuit? I. So what is the net resistance now? R1 plus R2. So this I'll represent it as R equivalent. Understand now? So R equivalent is equal to R1 plus R2. So if I generalize this expression, if there are n resistors which do carry same current, then they are considered to be in series, and their equivalent resistance is R equivalent is equal to R1 plus R2 plus R3 up to R. So they are like this. Same current is flowing through them. Then their equivalent value is R1 plus R2 plus R3 plus R. So this is the generalized expression. Now, the next one is resistances in parallel. So this is a representation of resistances in parallel. Okay, so now here in this circuit you see 2 resistors are there. They are connected such that the potential drop across them, see this is the potential drop across them, V1. This is the potential drop across them, V2. The potential drops across them is same. They are between the same node A. Nothing is there between them. These type of resistors which have same potential drop across them are termed as parallel. They are to be considered that they are connected in parallel. They are between the same points. See, this is between this and this. It is also between this and this point. Understood? So in this case, now let us suppose the current which is flowing is I, and it is divided into I1 and I2. Okay. So if I take at this point, so I will, this is I, this is I1, and this is I2 at this particular node A. So by KCL, I plus, this is incoming current, these two are outgoing currents, so I have taken as minus I1 and minus I2. So I incoming current is equal to outgoing current. This is by KCL, right? Then what is I1? You know it. It is V by R1. Same potential drop across there. Right. So what is I1? V by R1. What is I2? V by R2. So if I substitute them, this is the equal. Right. So now if I take this as an equivalent resistance, I is equal to V by R equivalent. So this is already equal to V into 1 by R1 plus 1 by R2. Right. So if I equate them, what I'll get? 1 by R equivalent is equal to 1 by R1 plus 1 by R2. If I generalize this expression for parallel connected resistors, what is the equivalent resistance? 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by R1. Try to remember this point. Once again, I'll repeat it. If the resistors are connected in series, means they are carrying same current, and their equivalent value is R1 plus R2 plus R3. If the resistors are connected between the same ends, or they do have same potential drop across them, then their equivalent resistance is, this is the equivalent resistance. Okay. So with this, I will close the session, and in the next session, we will solve problems on